Physics 2211 Lab 2, Motion of a Falling Object. The purpose of this experiment was to observe the motion of a falling object dropped from rest and model that data using tracker software. Then create a computational model in GlowScript with and without drag, and then compare the results of the three. The fundamental principle involved is Newton's second law, force equals mass times acceleration, also known as the momentum principle because force is equal to the change in momentum over the change in time. In my experiment, I had my sister drop a tennis ball from the back porch. I chose this because the higher I drop the ball from, the longer it is in the air, and the tracker software will be more accurate, as it has more frames and therefore more data points to extrapolate from. Here I have the tracker data and the graph of position versus time on the right. As you can see, the slope becomes more and more negative, indicating an increase in velocity. I chose a tennis ball because the neon yellow stands out and makes the job easier for tracker. I've also listed the properties of the ball used in the following equations. The net force on the ball is equal to the weight minus the drag. Weight is mass times gravity, and drag is this long equation. I included the actual equation just to show you, but for simplicity's sake, we'll treat drag as b times velocity squared. Momentum is equal to mass times velocity, and force is equal to change in momentum over the change in time. Now I'm going to get the velocity update equation needed for my GlowScript code from the momentum principle. Force is equal to the change in momentum over the change in time. So force is equal to mass times v2 minus mass times v1 over change in time. Force times change in time is equal to mass times v2 minus v1, all the way down to force times change in time divided by mass plus v1 is equal to v2. And force equals weight minus drag, so force equals mg minus b v1 squared. Finally, giving us the total equation, mass times gravity minus b v1 squared times delta t over mass plus v1 is equal to v2. Here are the position versus time graphs of the observed data, the computational data without drag, and the computational data with drag. As you can see, the orange graph reaches 0 before the other two. This is because without drag, the velocity increases more quickly. The computational with drag is much more closer to the observed data. The difference could be from a small mistake made in tracker, or the b from the drag equation not being exactly correct. The computational model with drag approaches a terminal velocity because once d equals w, the net force is 0, and the velocity update equation becomes 0 plus v1 equals v2, therefore no longer increasing. If the object was thrown, it would reach the same terminal velocity, but it would reach it sooner than drop from rest. The graph of starting from rest is on the left, and the graph starting with a velocity of -2 meters per second is on the right. Both graphs result in the same slope, but the right reaches it sooner.